Hello everyone! Today we'll be presenting and talking to you all about the frog sciatic nerve. We are group number 3, our section is Monday and Wednesdays, and our TA is Adam. My name is Ton Chao Chu.
My name is Quinn Ha.
And my name is Christy Lee.
First of all, we have to dissect the frog to remove the sciatic nerve. Remove the skin of the frog and separate the muscles of the thigh. You see that the sciatic nerve runs from the lower back to the knee joint and is white in color, although it's shown in black here. Tie sutures at each end of the nerve and remove the nerve from the frog. Now you have your nerve that's ready to be put into the nerve chamber for experimentation.
3 different drug treatments were used on the frog sciatic nerve. 30 millimolar of high calcium ringer, 0.5 millimolar of Verapamil, and 20 micrograms per milliliter of Amiodarone were used. High calcium ringer is a sodium channel blocker that's proven to be essential to life but is toxic to the sciatic nerve in high concentration. Verapamil is a calcium channel blocker that's proven to cure hypertension, heart attacks, and help with kidney problems. Amiodarone is a multiple ion blocker that treats cardiac arrest and arrhythmias. Based on their mechanism of action, we expect that high calcium ringer would decrease excitability, that Verapamil would have no effect on the sciatic nerve, and that Amiodarone would increase excitability.
Here are the results for high calcium ringers. For the control, the threshold was between 60 to 65 millivolts. Maximum cap was 4.74 millivolts, and conduction velocity was 45.45 meters per second. After the treatment, the threshold was between 80 to 85 millivolts. Maximum cap was 2.7 millivolts, and conduction velocity was 24.39 meters per second. So overall, there was decreased nerve excitability, decreased speed of conduction down the axon, and less nerve fibers were recruited at the same stimulus potential. This graph shows the effect on refractory period after treatment with high calcium ringers. The difference in cap amplitudes decreased as the impulse interval increased. Just as a reminder, a stimulus delivered during the absolute refractory period of a neuron would not result in an action potential. There was a decrease in difference between the cap amplitudes, which means that the second cap amplitude increased and that the second stimulus initiated action potentials in more neurons and that less neurons were in their absolute refractory period. So overall, this graph shows that the refractory period decreased after treatment with high calcium ringers. When a neuron is at rest, there are more potassium ions inside the cell and more sodium ions outside. The membrane is much more permeable to potassium ions due to more potassium leach channels. The resting membrane potential of a nerve is approximately negative 70 millivolts, and the membrane potential is the electrical potential difference between the inside and outside of the cell. The inside has a net negative charge since more positive charges leave than enter. Consequently, the outside has a net positive charge. Leach channels allow for both sodium and potassium to cross in and out of the membrane, and the sodium-potassium pump reestablishes the resting membrane potential by actively transporting 3 sodium outside of the cell for every 2 potassium inside of the cell against their electrochemical gradients. The threshold to fire an action potential in a neuron is around negative 55 millivolts. A stimulus big enough to reach threshold would trigger depolarization of the membrane. Once stimulated, the inside of the membrane becomes more positive than the outside. This change in membrane potential triggers activation of voltage-gated sodium channels and allows sodium ions to flood into the neighboring areas of the membrane and spread the depolarization. Voltage-gated potassium channels also activate in response to depolarization of the membrane, but they open slower than voltage-gated sodium channels. Once voltage-gated potassium channels open, potassium ions rush out of the cell, repolarize the membrane, and re-establish the resting membrane potential. High cellular calcium level causes the outside of the cell to be more positive, increasing the difference in potentials between the inside and the outside, and causes resting membrane potential to decrease. This makes it harder to activate voltage-gated sodium channels because it is harder to depolarize the membrane. Once an action potential is fired, calcium can also block voltage-gated sodium channels, which leads to less permeability to sodium and less contribution to the electrotonic current that drives the action potential across the axon. This leads to less activation of neighboring voltage-gated sodium channels, thus conduction velocity of the action potential across the axon decreases, and excitability of the neuron also decreases. Calcium also increases the inactivation rate of voltage-gated sodium channels. This means that voltage-gated sodium channels are open for a shorter time, and depolarization of the membrane does not last as long. Since depolarization does not last as long, the action potential amplitude does not go as high, so the maximum cap amplitude decreased. The repolarization to resting membrane potential will take the same amount of time since the membrane is not as depolarized, but resting membrane potential was also lowered. Refractory period is the period of time at which voltage-gated sodium channels are inactivated and a second stimulus will not elicit another action potential. Sodium channels reset to their resting conformation as a result of repolarization. Since voltage-gated sodium channels inactivate earlier and repolarization, or the time it takes for them to reset to their resting state, is the same, overall, the refractory period decreased.
Verapamil was added to the nerve chamber to be soaked for about 5 minutes. The stimulus potential to reach threshold produces a cap from between 120 and 125 millivolts for both control and treatment of verapamil. The max cap for the sciatic nerve was 5.165 millivolts, and the max cap for sciatic nerve was 4.91. Meanwhile, conduction velocity had a control speed of 35.71, while verapamil had a speed of 31.25. Overall, we see a trend of a slightly decreased threshold and conduction velocity. Here is the refractory period for verapamil treatment, where the dark green represents the control and the light green represents after the treatment. As you can see here, the cap amplitudes show both before and after treatment, where the second cap amplitude was higher than the first cap amplitude, and the difference in cap amplitudes showed very minimal change both before and after treatment. Most of the data points here overlap with each other, and the overall trend is that the refractory period did not have a significant difference between the control and treatment of verapamil. With the nerve, there exists extracellular and intracellular space, which will shorten by outside and inside. For action potentials, typically sodium and potassium are involved for depolarizing, making the membrane potential more positive, and repolarizing, making the membrane potential more negative. But because verapamil blocks specifically calcium, there is no effect on the threshold of the action potential. There are calcium channels located at the end of the axon terminal, which is what triggers synaptic exocytotic vesicles to release neurotransmitters, but that does not impact the action potential along a nerve axon.
The stimulus potential need to reach threshold was 35 millivolts for the control, and it decreased to 30 millivolts after amiodarone. The cap amplitude recorded when a stimulus of 1 volt was applied was 5.395 millivolts for the control, and it increased to 6.31 millivolts after amiodarone. The conduction velocity increased from 35.71 meters per second to 90.90 meters per second. There was a decrease in the stimulus needed to reach threshold, and an increase in the cap amplitude at each respective stimulus potential, which means that the nerve excitability increased, fiber recruitment increased, and also the speed down the axon increased. The difference in cap amplitudes were measured between interpulse intervals of 0.75 and 10 milliseconds. The trend for the amiodarone condition was higher than that of the control, meaning that the difference in cap amplitudes had increased after treatment. The difference is calculated by subtracting the second cap from the first cap, meaning that the second cap had decreased at a faster rate, higher and longer interpulse intervals compared to that of control. This means that the action potential durations had increased, providing for longer refractory periods, meaning that amiodarone must have affected the voltage-gated sodium and potassium channels on the nerve. Amiodarone blocks sodium and potassium leak channels on the membrane, and the membrane potential depends on the net flow of sodium, potassium, and chloride ions through leak channels at rest, and is calculated by the difference in ion concentration between the intercellular and extracellular environments. Sodium channels move sodium in, while potassium leak channels move potassium out. The membrane has more potassium leak channels than sodium, so more potassium ions leak outside the membrane at rest than sodium can move in to balance the membrane potential. So the resting membrane potential is normally around -70, while the threshold is around -30. When amiodarone blocks both leak channels, less sodium ions can leak inside, but more importantly, even less potassium ions can leak outside. This increases the resting membrane potential closer to threshold because there are less leak channels open to decrease the resting membrane potential all the way to -70. Therefore, the membrane potential becomes less negative, which makes it easier for a greater potential to depolarize the membrane to threshold and initiate a cap, which explains why the stimulus needed to reach threshold decreased, since the neurons did not need as strong of a stimulus with the membrane potential already near threshold. The nerve was able to recruit more fibers at each stimulus potential because all the fiber types were more excitable, and therefore each stimulus was able to excite and trigger even traditionally less excitable fibers to fire action potentials increasing and producing larger caps at every stimulus potential. Conduction velocity depends on the speed at which sodium ions flood into voltage-gated sodium channels during depolarization and spread as the electrotonic current to neighboring voltage-gated sodium channels to depolarize them. Normally, the spread of the electrotonic current weakens as the action potential gets regenerated down the axon, because sodium ions that flood in through voltage-gated channels usually leak out of the nerve through leak channels because they're attracted by the negative charges that line the outside of the nerve membrane. The local current does not produce a strong enough depolarization to bring the membrane to threshold, so it takes time for the ions to build up again enough to conduct an action potential at the next sodium channel. However, axons usually have a myelin sheet that essentially blocks a lot of the leak channels, allowing the action potential to hop from one node to the next, and this maintains the strength of the action potential and increases the speed of conduction. By blocking the sodium leak channels, amiodarone essentially does the same thing as myelin, strengthening the electrotonic current spreading to neighboring voltage-gated sodium channels, since less sodium ions are able to leak out, so the local current is stronger. The axons of the neurons had myelin during the control condition, but amiodarone was able to block even more leak channels at the nodes on the axon that were not blocked by myelin already. Ultimately, amiodarone made it easier for the beta potential to depolarize the membrane to threshold and faster for the action potential to be regenerated as it moved down the axon, producing the faster conduction velocity. An action potential cannot be fired until the greater depolarization brings the membrane potential to threshold, and upon activation, voltage-gated sodium channels open to allow sodium ions to flood in and depolarize the nerve, while potassium channels allow potassium ions to flood out, causing repolarization of the action potential. When amiodarone blocked many of the voltage-gated sodium channels, more time was required to depolarize the nerve completely, since only some sodium channels were able to be activated by the voltage reaching threshold and allow sodium ions to flow into the nerve. Once the peak of depolarization was reached and voltage-gated potassium channels were activated, many were again blocked by amiodarone, so potassium ions were only able to flow out through some of the channels, which prolonged the time it took to repolarize the nerve membrane completely. Since the refractory period is the time between the start of depolarization and the end of repolarization before hyperpolarization, the longer it takes the membrane to depolarize and repolarize for sodium ions to move in and potassium ions to move out, the longer the duration of the action potential is, and the longer it takes for each neuron to get out of its refractory period. Only after the neurons are out of the refractory period can they be stimulated again by a pulse, which is why the amplitude of the second cap dropped faster at longer intervals compared to that of the control condition. To summarize, high calcium ringers decrease the resting membrane potential because of the increase in positive charges outside of the membrane, and it blocked and stabilized the resting conformation of sodium channels, which decreased their activation, which in turn decreased excitability and the conduction velocity and increased the stimulus needed to reach threshold. In increasing the inactivation of sodium channels as well, it decreased the action potential duration, which decreased the refractory period. Verapamil blocked calcium channels in the neuromuscular junction, and since there are no calcium channels on the nerve membrane, there was no significant effects on the excitability, conduction, or action potential of the nerve, so the threshold, maximum cap amplitude, conduction velocity, and refractory period remained relatively the same. Amiodarone blocked the leak channels, which increased the resting membrane potential, which in turn increased excitability, which decreased the stimulus needed to reach threshold and increased the conduction velocity. It also blocked the voltage-gated channels, which decreased the rate of depolarization and repolarization, which increased the action potential duration, which in turn increased the refractory period. That concludes our presentation.
Hopefully, you were able to learn something new and found something interesting about these drugs discussed today.
Thank you so much for listening.